So when thermal kinetic energy is added to an object, the object's temperature often increases. So that means that when you add heat to an object, the temperature goes up. So that is something we expect to hear. It doesn't always happen, but when it does, the size of delta T, the size of the change in temperature, depends on how much heat energy was added, the object's mass, and the object's composition. So it depends on all three of those things. And if we use so let's think about this with some examples. If we use a match to heat a large glass of water, then the water temperature doesn't go up very much. You can imagine that using just a little match, a little flame, to heat up a large beaker of water doesn't do very much. But if we heat up a needle or any piece of metal using a match, the needle gets hot. So there's a big difference here, even though the amount of energy we're adding should be the same because it's coming from the same source, a little match. The needle is hotter because it has a smaller mass than the glass of water, and because metal has what we call a lower specific heat capacity than water. The specific heat capacity is the amount of energy that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So this is our equation down here. C, which is what we call the specific heat capacity, has units of joules per gram per degree Celsius. And we calculate it by dividing the heat energy, Q, which we learned about in the last section, by the mass in grams and the change in temperature. So let's look at that some more. Specific heat capacity has units of, like I said, joules per gram per degree Celsius, or you can also say it has units of joules per gram per Kelvin. So because degrees Celsius and Kelvin, they typically would have a different effect on our calculation, but because it's a temperature difference, 1 degree Celsius difference and 1 degree Celsius or 1 degree Kelvin difference is the same, because these two units are only different by a matter of addition. So you add 7 degrees to your Kelvin to degrees in Celsius. Because it's an addition, when we have a difference, the difference doesn't matter. So whether it's 1 degree Kelvin making 274 degrees Celsius, then that's a 1 degree difference from 273, or a 1 degree difference from absolute 0. All right, so moving on, most metals have low specific heat capacities. We have a table of some commonly known heat capacities here on the right. So metals like aluminum, iron, copper, gold, they have low heat capacities compared to water or ice, or even some other liquids like ammonia and ethanol. So you can see gold has a very low heat capacity. So when we heat up gold, it raises its temperature very rapidly. Other materials like water have high specific heat capacities, which means that you need to add energy to get the same temperature increase. And what this means from a practical standpoint is you could use the same amount of heat energy and it would raise the temperature of 1 gram of gold 30 times more than it would raise the temperature of 1 gram of water. So heat has a bigger effect on things with lower heat capacities. All right, and here is a little demonstration of what that looks like. So because we said it's based on, so the amount of temperature change is based on the mass, the heat added, and the composition, we're going to just change composition in this experiment. So like you learned back in experiment 7, we should only change one variable at a time. So we're keeping the amount of heat added constant. So that's 150 joules of heat being added from our Bunsen burner. We're keeping our mass the same as well, 5 grams of our substance. The thing that we're changing is the composition. So our material is copper on the left and glass on the right. And this is how you can determine the specific heat capacity of different materials. The copper temperature increased much more than the glass temperature. So the final temperature, they both started at 20 degrees Celsius. The final temperature of copper is 97.9 degrees Celsius. The final temperature of glass is only 55.7. So the temperature of the glass did not increase as much as the temperature of the copper, telling us that copper has a smaller specific heat capacity. It's easier to raise the temperature of copper. All right, so now we're going to use some data and determine a specific heat capacity. So if we go back to that first slide, we see that our formula is C, the specific heat capacity, is equal to Q, the heat added, divided by the mass times delta T. So that is the same as T final minus T initial. So if we plug that in, we're going to get, so 94.4 joules is our Q. Our mass is 14.4 grams of nickel. And our delta T is going to be 37.2 degrees minus 23.4 degrees Celsius. So if we plug that into our calculator, we see 94.4 divided by 14.4 divided by our parentheses 37.2 minus 23.4. And we find out that the specific heat capacity of nickel is 0.475. And our units are joules per gram degrees Celsius. Because we have joules on top, grams on the bottom, and degrees Celsius on the bottom. So there you go. That's how you calculate specific heat capacity. So we can keep going and talk about specific heat capacity to determine the amount of heat that is required to go from one temperature to another, or the final temperature when we've added a certain amount of heat. So for A, we're going to determine the amount of heat energy associated with heating a 14.6 gram sample of solid aluminum. So aluminum has a heat capacity of 0.900 joules per gram degrees Celsius as given in the problem. And that is going to be equal to Q over the mass times the change in temperature. So for A, we're solving for Q. So I'm going to put Q by itself, and we're going to multiply M delta T to the other side. All right, so Q is going to be equal to our specific heat capacity, 0.900 joules per gram degree Celsius times our mass, which is 14.6 grams, times our change in temperature. So going from 22.5 degrees Celsius, that's our initial temperature, to 36.7 degrees Celsius as our final temperature. And if we plug all that in, our grams and our degrees Celsius are going to cancel out, and we're left with joules. So 0.9 times 14.6 times parentheses 36.7 minus 22.5. And I got that we need to add 187 joules of heat to achieve that temperature change from 22.5 Celsius to 36.7 degrees Celsius. So that's part A. 187 joules of heat is required. And now for part B, we're going to instead find the final temperature after we've added 1.28 times 10 to the third joules. So now, again, we're going to use our heat capacity equal to 0.900 joules per gram degrees Celsius. So we have that equal to Q over M, and I'm going to write it out this time, T final minus T initial. So this time we want to get T final by itself because they told us what the initial temperature is. So I'm going to take Q over M and multiply by the reciprocal, M over Q, so we can get that on the other side. So 0.900 joules per gram per Celsius. And we're going to multiply that by our reciprocal, so M over Q. So 21.4 grams over our 1.28 times 10 to the third joules was our Q. And that is going to be equal to T final minus T initial. So we just have to add T initial to the other side to get T final by itself. So I'm going to do that multiplication first and then add our T initial. So if we do that, we have 0.90 times 21.4 grams divided by 1,280 if we move that decimal place over a 3 to get into our standard notation and not scientific notation. So for that, I got 0.0150, and that has grams canceled out. Oh, I'm so sorry. This should still be all under our denominator, huh? Okay, so we've got our grams and our joules canceled out. So our 0.0150 is still in units of 1 over degrees Celsius. And that's equal to 1 over T final minus T initial. So let me rewrite this a little bit. So I've got 0.0150, and that's 1 over Celsius, is equal to 1 over T final minus T initial. So we couldn't move our T initial over just yet. We have to take the reciprocal of everything, which is the same as saying we want to multiply T final minus T initial by this side, and we want to get it to the other side. So that means we're going to have T final minus T initial, times 0.0150 is equal to 1. So now we just have to divide both sides by our 0.01501 per Celsius. So we divide 1 by that. We just take the reciprocal of 0.0150. And that gives us T final minus T initial is equal to 66.7 degrees Celsius. So that means that the difference between the two, so the difference between the final and the initial temperature, the change in temperature is 66.7 degrees Celsius. So we just have to add 66.7 degrees Celsius to our initial temperature to find our final temperature. So 22.5 degrees Celsius plus 66.7 degrees Celsius gives us our final answer of 89.2 degrees Celsius is our final temperature. So I apologize for doing that a little bit backwards. So just to reiterate, we wanted to, so we had our C, we had our Q, we had our mass, and we had our T initial. So we could plug all of those in and solve for T final. So if I write that all out again, you guys can see how it was solved. So we get 21.4 grams, and our X minus T initial. We were solving for X. All right, so that's how you do it if you guys want to try it at home. All right, so if we keep moving on, we're going to talk about heat transfer and thermal equilibrium. Heat transfer is when objects with different temperatures touch each other and the hot object transfers thermal energy to the cooler object. So think of this like if you give your friend a hug and your friend just came in from a really hot day outside. And they're really warm and you've been in the air conditioning all day. So when you give each other a hug, their warmth goes into you and so they heat you up and you cool them down. So the hotter object cools, the cooler object warms, and this process occurs until the two objects reach the same temperature. So after a while, if you are, so you probably wouldn't want to hug someone this long, but if, for a different example, you take a hot towel out of the dryer, like fresh out of the dryer, and you wrap yourself in it, eventually it's going to be really warm anymore. You're going to warm up, the towel's going to cool down, and eventually you're going to be at room temperature again, both you and the towel. So that is what we call thermal equilibrium. And during this heat transfer, the heat energy that's lost by the hotter object is equal to the heat energy that was gained by the cooler object. So this hot towel you pull from the dryer is going to warm you up and it to lose its heat to you in the same quantity of the heat that you gain from it. So negative Q lost is equal to positive Q gained. Or if you want to write it a different way, Q lost plus Q gained equals 0. So if we look at an example down here, we have a block of wood and a block of aluminum metal. The wood is 25 degrees Celsius. The metal has been heated. so it's at 75 degrees Celsius. And when we put them next to each other, they come to an equilibrium of 41.9 degrees Celsius. So not quite in between the two, because our two materials have different heat capacities. So you got to remember that. That the heat that is exchanged isn't quite the same as the temperature difference. So if we consider a heated iron bar that we put in a glass of water or a beaker of water, we're going to define the iron as our system and the water as the surroundings. So if the iron is the system and the water is the surroundings, then the process is exothermic, because the heat energy that's lost by the system is gained by the surroundings. So we see that in our figure here. The initial state of the iron has a high enthalpy. It had a lot of heat energy. The initial state of the water had low enthalpy. It had low heat energy to begin with. It was cool, the iron was hot. So when we put them together, the iron cools down. So we have a loss of heat from the iron, and the water heats up. We have a gain of heat by the water. So this is a heat transfer from iron to water, and the iron is losing heat, so it's a negative change, and the water is gaining heat, it's a positive change. But when we add it all together, the positive heat gained and the negative heat lost is still equal to 0. The heat is not created or destroyed, just transferred between the two parts of between the system and the surroundings. Sorry. All right, so let's look at another example. We have a 12.73 gram block of solid platinum, which is at 10.37 degrees Celsius, and we put it in a pool of liquid propylene glycol at 24.56 grams, and that has a temperature of 60.81 degrees Celsius. So what is the temperature of both when thermal equilibrium is reached? So again, our formula that we're going to need here is that Q negative, we'll say Q negative of platinum, is equal to Q of propylene glycol, which I'll call PG. Okay, so how do we calculate these Qs? So we are given a heat capacity for both. We're given masses and temperatures for both. So let's write this out. So our C platinum is going to be equal to our Q platinum over our mass of platinum and the temperature. So our final temperature is X, and our initial temperature was 10.37 degrees Celsius. And our heat capacity of propylene glycol is going to be the heat gained by propylene glycol, or vice versa. The propylene glycol started out hotter, so it's probably actually the one losing heat. So we'll call that one our negative when we get there. And then it's divided by the mass of propylene glycol times, again, X minus our initial temperature, 60.81 degrees Celsius. All right, but because these two are equal to each other, equal and opposite, we're going to say, I'm going to be able to write my whole equation as so we have our C platinum is 0.133 joules per gram degrees Celsius, and it's going to be equal to Q platinum over 12.73 grams times X minus 10.37 degrees Celsius. So I'm going to solve that for Q. So I'm going to multiply both sides by the stuff on the bottom. So we're going to get Q platinum is equal to 0.133 joules per gram degrees Celsius times 12.73 grams times X minus 10.37 degrees Celsius. So that's our Q platinum, and it's going to be equal to negative QPG. All right, so we've got to do the same thing for QPG. So I'm going to do that up here. So 2.50 joules per gram degree Celsius is equal to QPG over 24.56 grams times 6, so X minus 60.81 degrees Celsius. And we multiply sides with the stuff on the bottom. So we're going to see that if this is negative QPG, then this has to be negative. So it's going to be equal to negative 2.50 joules per gram degrees Celsius times 24.56 grams times X minus 60.81. All right, so now I'm going to rewrite this. It's a long one, so we're going to need a lot of room. All right, so we've got our 0.133 joules per gram degrees Celsius. And that is going to be times our 12.73 grams of platinum times X minus 10.37. And that's going to be equal to our negative 2.5 joules per gram Celsius times 24.56 grams times X minus 60.81. All right, so our grams are going to cancel out. So we can get rid of that. And now let's simplify a little bit. So we've got 0.133 times 12.73. So I'm going to say that's 1.693. And that's going to be joules per degree Celsius times X minus, going to multiply that by 10 now, our 10.37. So that's going to be 17.56. And that's just joules because this one was degrees Celsius. Is equal to, and we do the same thing on the other side, 2.5 times 24.56 is, we'll put our minus sign in, 61.4 joules per degree Celsius times X. And then we're going to have a plus because we have a minus here and a minus here. So our 61.4 times our 60.81 0.81 is going to give us 3,734 joules. All right, so we've got 1.693 joules per degree Celsius times x minus 17.56 joules equals minus 61.4 joules per degree Celsius x plus 3734 joules. All right, so now let's move our x's all to one side and our joules all to the other side. So I'm going to add our 61.4 plus our 1.693. So we're going to add this to the other side, and we're going to get 63.093 joules per degree Celsius x is equal to, we add our 17.56 joules to the other side, and we're going to get 3734 plus 17.56. So I'm going to say that's 3752 joules. So now if we divide by our 63.093 joules per degree Celsius on both sides, then our joules are going to cancel out and our degrees Celsius are going to move to the top where we want them. So what is 3752 divided by 63.093? And I'm going to erase and write our final answer. So the final temperature, dF, is going to be equal to 59.5, well, we'll say 59.46 degrees Celsius. So the propylene glycol didn't go down too much in temperature. The solid platinum went up a lot. Does that make sense? Yeah, that makes a lot of sense because platinum is a metal and propylene glycol is a solution. It's a liquid, so it doesn't have nearly as high specific heat as platinum. So platinum can raise its temperature very quickly when in contact with something hot, whereas propylene glycol's temperature doesn't go down very much.